Okay, we're going to continue with chapter 10. Right now, and we're doing reactions. There are different ways of carrying out the reaction. One way is you could use stoichiometric quantities. And so when we're adding just the right amount, so let's say we're doing this reaction between zinc solid and hydrochloric acid, HCl. What kind of reaction does this look like here? Single replacement. And this should be a decent single replacement reaction. Zinc is a pretty good reducing agent. You know, chloride is pretty stable, it's going to be a spectator. So just H plus and water. The water is not going to be nearly as reactive as zinc or H plus. And so we can just go ahead and do this. This is going to form zinc chloride and hydrogen gas. Zinc chloride is aqueous, hydrogen gas. What's the driving force for this reaction here? Is it gas formation? Is it the driving force? Gas formation helps, but it's not the stronger acid, the weaker acid. No, you know, gas formation, stronger acid, weaker acid, precipitation, those are all driving forces for metathesis and acid base. This is, we're going to go from stronger reducing agent to weaker reducing agent. So more active to less active reducing agent or element. And likewise, the oxidizer, H plus is a stronger oxidizer than CN2 plus. So those are driving force for this reaction. Now, if we had stoichiometric quantities, then, you know, for every mole of zinc, how many moles of HCl do we want? We want 2 moles of HCl. And so, the problem with that is it's difficult to measure. You know, how can you measure it to the atom, you know, or to the molecule? You know, how can I get it perfect? So, in other words, let's say for every zinc atom I need 2 molecules of HCl. Okay, that's no big deal, but let's say if I had 1 mole of zinc, that's 6.022 times 10 to the 23rd, right? Am I going to hit it just right on 12.04 times 10 to the 23rd? And so in order to get stoichiometric quantities, then we need just the right amount. Getting just the right amount is very difficult. You aren't going to be sitting there measuring it molecule by molecule until you add just the right amount of HCl. And so what happens typically is this. Stoichiometric quantities are exactly the right amount, or just the right. Instead, what typically happens is we'll have excess and limiting reactants. And so it depends, you know, let's add in some zinc and then add a little bit extra HCl to make sure all the zinc reacts. Or let's add in some HCl here and then add in some extra zinc to make sure there's no HCl left. We don't want to add in too much excess because that would result in a waste. And so let's take a look at number 44 here in the homework. This is doing it in 3 ways. The plots below illustrate 3 trials of a reaction between varying amounts of zinc and a constant volume of hydrochloric acid solution of a constant concentration. The table gives the initial amount of zinc added and the observation conclusions of each. So in the first flask here, what they did was they add some zinc in here and generate hydrogen gas. When you look at this, this has stopped reacting, so no more bubbles of gas are forming, and we have some leftover zinc. That leftover zinc is called excess zinc. That means what has had to happen is all the HCl must have reacted, and so there's no more HCl to react, otherwise the zinc would continue to react. And so in this case, the excess reagent or reactant, reagent-reactant, we will use those those terms interchangeably. The excess reactant is zinc. The limiting reactant is HCl. And at this point, all the HCl is gone. There's no more reaction left. If there's no more HCl, there's no more reaction. And then we have some left over. And so all that HCl is reacted to form the hydrogen gas shown here. Okay, this is excess. Over here in flask 3, we have excess HCl and not enough zinc. All the zinc has been eaten away. There's no more zinc left. But you can tell not all the HCl is reacted because we had the same amount of HCl as this flask and we generated less hydrogen. And so that means there's still some HCl left in here. So if we add some more zinc to this, we can generate more hydrogen gas. And so in this case, the excess reactant is HCl, the limiting reactant is zinc. In flask 2, this is what we call stoichiometric. In flask 2, we added just the right amount of zinc and we have just the right amount of HCl. And so there's no more zinc left and all the HCl is reacted because this is how much hydrogen we should form if all the HCl is reacted. And so these are 3 ways of doing the reaction. So here they added 6.10 grams of zinc, which is excess. The balloon inflated completely, some unreacted zinc remains. So all the HCl has been consumed. We have excess zinc. Here in the third scenario, they added 0.41 grams of zinc, not enough zinc. All the zinc is reacted, but there's still some HCl remaining, as we can tell because we didn't generate as much hydrogen. Here, this is a stoichiometric amount of zinc, so we call 2.37 grams the stoichiometric amount of zinc for this reaction because this is just the right amount of zinc. When we're dealing with stoichiometric quantities, it's just the right amount. And so we react all the zinc, none's left over. We react all the HCl, none's left over. When we have excess and limiting, one of these is an excess. And the limiting reactant is always consumed. And so limiting completely consumed. In the reaction, and the excess is left over. So normally, it depends on what we want to happen in this particular reaction. Sometimes we'll play it safe by adding it. So if we want all the zinc to react, then typically what we'll do is we'll add excess HCl. If we add excess HCl, get all that zinc to react, and there's no more zinc left. If we want all the HCl to react, then we'll add excess zinc just to make sure, because it's hard to get it right at stoichiometric perfectly. I mean, we might have just a slight, very slight excess of one or the other. So that's the whole concept between when you're measuring these things out, it's a bit of a hassle to measure it out stoichiometrically. So typically what we'll do is we'll keep one at excess, a slight excess.
How can you tell from just the equation? Can you?
You can. The equation just tells us the stoichiometric ratio. So the equation tells us just the right amount. But when you're in lab, it's hard to measure. Yeah. Sometimes. All right, so let's try out some limiting reactant problems here. For example, like number 45. A solution containing 1.63 grams of barium chloride is added to a solution containing 2.40 grams of sodium chromate. The reactions between barium chloride and sodium chromate. Let's try that. So what's the formula for barium chloride? Yeah, BaCl2. Sodium chromate. Na2Cr04. All right, which form here? Let's look at AB plus CD metathesis reaction. We're going to form barium chromate and sodium chloride. So we'll need 2 of those to balance that. Chromates are all insoluble except for group 1 and ammonium, so this is going to be a precipitate. All sodium salts are soluble. We have a driving force here. So what we're going to add is barium chloride. We're going to have 1.63 grams here. And then the sodium chromate, we're going to have 2.40 grams. Can you tell by looking at this, is this stoichiometric or do we have excess, limiting? We can't tell. You know, and so what we're going to do is we're going to figure out. And the way we're going to figure this out is we're going to figure out by what we call the there are two methods that are used in the book: comparison of moles and maximum yield. And so we're going to do the yield amount. So we're going to go from 1.63 grams of barium chloride, and then we're going to go to moles of barium chloride. And from moles of barium chloride, we're going to go to moles of product. And from moles of product, then we're going to go to grams of product. So this is barium chromate. I'm running out of room here. Grams of barium chromate. And then what we call this is, we call this the yield from barium chloride. Assuming we have plenty of sodium chromate to react with. Yield from barium chloride, assuming there's enough sodium chromate. Okay, then we're going to do a similar calculation where we're going to go with 2.40 grams of sodium chromate. Then what we're going to do is we're going to go to moles of sodium chromate here. And then from moles of sodium chromate, we're going to go to moles of barium chromate. And then from moles of barium chromate, we're going to go to grams of barium chromate. This is going to be called the yield from sodium chromate. Yield from sodium chromate. And so what we're doing here is this. We're just going to completely react. If we completely reacted all 1.63 grams of barium chloride, how much barium chromate would we form? And then we'll do another calculation. If we completely react all the sodium chromate, how many grams of barium chromate will form? And then we pick the smaller amount. Pick the smaller amount. Because once one of them has completely reacted, there's no further reaction that takes place. The smaller amount, this is called our theoretical yield. Just write it over here. Theoretical yield. That's because in theory, we can't form more than this because once one of these have completely reacted, then there's no more left for further reaction. And the reaction's done. And so, okay, let's go ahead and do this. So this is a limiting reagent problem. All limiting reagent problems is you're given amounts, multiple amounts. Here. So you can recognize a limiting reagent problem is you're given multiple amounts of product. If we only had a single amount, let's say this would be an example of a non-limiting reagent problem. A solution containing 1.63 grams of barium chloride is reacted with a solution containing sodium chromate. And so they only gave you the amount of barium chloride, they didn't give you the amount of sodium chromate, and so therefore we can assume we have plenty of sodium chromate to react, and we aren't going to worry about it. But we're given multiple amounts here, so we're going to calculate the yield from each of those amounts. And so one, we're going to get the yield from barium chloride. And here we have 1.63 grams. And so we start off with 1.63 grams of barium chloride, and then we need to convert that into moles. So we've got to figure out the molar mass. Barium has a molar mass of 137.33. 137.33. And then we have two chlorines. It's going to be 2 times 35.45. It's going to be 70.90. And so altogether, this is going to give us 3, 12, 8, 10, 208.3. And so each mole of barium chloride weighs 208.23 grams. And so the grams of barium chloride cancels, and that leaves you moles of barium chloride. And then we're going to do a mole-to-mole ratio. We're going to get 1 mole of barium chromate precipitate for every 1 mole of barium chloride that reacts. The moles of barium chloride cancels there. This comes from the balanced equation over there. And then we have to calculate the molar mass of barium chromate. Barium's 137.33. Chromium, and off this periodic table here, is 51, actually make that 52.00. Chromium is 52.00, and then 4 oxygens. It'll be 4 times 16.00 is 64. So we'll add these up. 3, 3, 6, 13, 253.33. So 253.33 grams of barium chromate for every mole of barium chromate. Let's cancel. So this should give us grams. This would be how many grams of barium chromate we could get if we were able to react all 1.63 grams of barium chloride. So this is going to be 1.63 divided by 208.23 times 253.33. That gives us 1.98. We'll allow 3 sig figs, so we'll go 1.98 of 3 grams of barium chromate. However, we don't know yet if we can get that much. We have to see, the yield from sodium chromate to determine that. And so 2, we'll calculate the yield from sodium chromate, the other reagent, Na2CrO4, and we had how many grams? 2.40 grams of this stuff. So 2.40 grams of sodium chromate, and we have 2 sodiums. We've got to figure out the molar mass. Sodium is going to be 22.99. 2 times 22.99 creates 45.98. We get a chromium, which is 52.00, and 4 oxygens, which is 64.00. That gives us 8, 9, 11. I got 161.98. So mole sodium chromate, 161.98 grams of sodium chromate. So grams of sodium chromate cancels, leaves us moles. And then it's a 1-to-1 mole ratio. So 1 mole of barium chromate for every 1 mole of sodium chromate. So moles of sodium chromate canceled using the moles of barium chromate. And the molar mass we calculated earlier, 253.33 grams of barium chromate per mole. There, so moles of barium chromate canceled. Let's see what we get for this one. Use this calculator. 2.4 divided by 161.98 times 253.33. 3.753. So what we're doing here is if we could react all the barium chloride, we'd form 1.983 grams. If we could react all the sodium chromate, we'd form 3.753 grams. And so we picked the smaller amount. So this is step 3. And the reason we picked the smaller amount is why do we pick the smaller amount? Why don't we pick the bigger amount? I'd like to pick the bigger amount because you get more barium chromate, but we can't pick the bigger amount. Why not? We can't pick the bigger amount because this is the maximum amount of barium chromate I can form if I react all 1.63 grams. So I'm going to react all 1.63 grams. Once all 1.63 grams of barium chloride is reacted, there's no more barium chloride left. If there's no more barium chloride left, then there's no more reaction. And so the reaction is going to stop here because we've run out of barium chloride at this point. And we have some excess sodium chromate. And so 3, pick the smaller amount. The smaller amount is 1.983 grams of barium chromate. And we call this the theoretical yield. This yield is not possible. Because we're going to run out of barium chloride. Okay. So what reactant is in excess? So what we do is we'll call this. Once we figure this out, then we know that barium chloride is called the limiting reactant, or the LR. And the sodium chromate is the excess reactant. A lot of people just say excess. All right, the next step is we want to determine how much excess reactant remains. Okay, as well as the mass in grams in excess of the amount required by the limiting reactant. So we're going to calculate the amount of excess reactant remaining unreacted. The amount of unreacted excess reactant. The amount of unreacted excess reactant is equal to the initial amount minus the amount consumed by the LR, the limiting reactant? Well, the initial amount is 2.40 grams. 2.40 grams of sodium chromate, what we started with, minus the amount consumed by the limiting reactant. Well, the amount consumed by the limiting reactant, well, what was the limiting reactant? The limiting reactant was the 1.63 grams of barium chloride. And so how many grams of sodium chromate does 1.63 grams of barium chloride require? And so we're just going to set this up stoichiometrically. What we're going to do is we're going to go 1.63 grams of barium chloride to, actually, no, maybe we'll do it this way. Barium chloride plus sodium chromate. So we'll do 1.63 grams of barium chloride. Then we're going to go to moles of barium chloride. From moles of barium chloride, we're going to stop here at moles of sodium chromate. And from moles of sodium chromate, we'll get grams of sodium chromate. And so this is how many grams of sodium chromate are required to react with 1.63 grams of barium chloride. And so we need to go from gram to mole conversion here. What was the molar mass of barium chloride? 137.33 grams.
So 1 mole.
Thanks. 1 mole. Okay, so grams canceled. That takes us to moles, and then we go to the moles of sodium chromate. It's a 1-to-1 mole ratio again here. So it's going to be 1 mole of sodium chromate for every 1 mole of barium chloride. So moles of barium chloride cancel, and then we are going to go to grams of sodium chromate. What was the molar mass of sodium chromate?
208.23.
208.23 grams of sodium chromate.
Hold on. Just kidding. Barium chloride. Oh, just kidding.
No.
Not 208.
Okay. That's it. I erased it. Yeah, barium chromate is 208.23. Sodium chromate was the 2 sodiums at 22.99 each. 45.98. Did somebody write it down? 161.98. 161.98. Okay, moles of sodium chromate cancel. That leaves us with grams of sodium chromate. This is the grams of sodium chromate consumed by the limiting reagent. So it's going to be 1.63 divided by 137.33 times 161.98. It's 1.92. So we had 2.40 grams initially, and the amount that's going to be consumed is 1.922 grams. Which means we're going to have 0.477 grams of unreacted sodium chromate. 0.477 grams unreacted sodium chromate. Why don't you try one then? There. Let's try number 46. This is an example of a Lewis acid-base reaction. Carbon dioxide Carbon dioxide can be removed from the air by reaction with potassium hydroxide. So carbon dioxide is what we call Lewis acid. Potassium hydroxide is the Lewis base. It's also a Bronsted base. Carbon dioxide is not a Bronsted acid. And so this is a Lewis acid base type reaction. And the CO2 reacts with KOH to form potassium. What's this called? Potassium
Carbonate.
and
Water.
water. So you need some molar masses there. But anyway, if 15.6 grams of carbon dioxide reacts with 43.0 grams of potassium hydroxide, so immediately they give you multiple amounts. If they give you multiple amounts, it's got to be a limiting reactant type problem. If it's a limiting reactant problem, then we're going to have to do the smaller amount method. And so why don't you give it a go? Let's go ahead and write the molar mass of CO2 first. The carbon is 1201. 2 oxygens, it's going to be 3200. And so CO2 is going to be 4401. And then KOH, potassium is 39.10. 39.10. Oxygen is 1600, and hydrogen is 101. And so KOH would be 5611. What product are we interested in? You know, if they don't tell us what product we're interested in, then we just pick one. In this case, they tell us we're interested in potassium carbonate, so we'll do potassium carbonate. But if they didn't specify one or the other, if they're just asking for which one's the limiting reactant, then we could pick the easier one, which would be water. I would have picked water here.
And would it be like 2 potassium, 2 oxygen, 2 hydrogens?
No.
That last part?
No.
No.
No. Yeah, it would be in this equation, right? But, you know, what's easier? Is it easier just to calculate it for 1 and then double it if they're 2 and triple it if they're 3? You know, that's easier. And so if I have 2 KOHs, I double this. 3 KOHs, I triple it. It's just easier calculating mass this way. We calculate it for 1, and then we'll double it later. We're going to double it in the dimensional analysis. We don't double it now, so we're ignoring these. We just want to know this. The stoichiometry is going to have it all figured out. All right. So you know, if they didn't specify which product, I would have picked water because it's quicker to calculate the molar mass of water. But they're interested in potassium carbonate. Well, calculating the molar mass of potassium carbonate is more hassle. So we got 2 potassiums. This could be 80, 79. Wait, 39. 78.20. 78.20. Carbon is 1201. And 3 oxygens. 16 times 3 is 48. 2 and 18. 12, 13, 138.21. K2CO3.
Sodium chloride is 208.23. The molar mass.
All right. That means I screwed it up. That calculation then, if barium chloride is 208, then it's going to change it. So rather than consuming 1.92 grams, we consume 1.27 grams. 208.2. Sorry, 208.2. gonna change this to 1.27 grams. And so the amount of excess remaining is going to be 1.13. 1.13 grams. Unreacted sodium. Thanks for catching that. This is the answer. All right, so let's go back to 46. Why don't you try 46? So what's your step one? Calculate the yield from calculate the yield from CO2. So you're going to go from what? You're going to go from grams of CO2 to from moles of CO2 to moles of potassium carbonate, and from moles of potassium carbonate to grams of potassium carbonate. So go ahead and do that calculation now. Let's see what you guys get. Were you able to get the first one?
Moles of potassium?
No, we're going to go to grams. All the way to grams. You could stop at moles, but since they're interested in potassium carbonate, we go all the way to grams. Did you guys get this or no? when we get to the KOH, then you'll see where we double it.
From the very beginning.
We don't double anything yet, but you'll see in a minute. But before we get to that one, what does this 48.99 grams mean here? What would you say this is in your own words? 48.99 grams of potassium carbonate. What does that mean? What is that number?
For every 48.99 grams of potassium carbonate, there's 15.6 grams of carbon dioxide.
Okay. For every 48.99 grams of potassium carbonate, you would have 15.6 grams of carbon dioxide. That works. Anybody else? Yeah. We create this much if we use this much. In other words, I call this the maximum yield of potassium carbonate from 15.6 grams of CO2. If we used all of it, this is how much we form. But we don't know if we'll use all of it, right? Because we don't know if we have enough KOH, the other ingredient. We need 2 ingredients for this, KOH. This is like if you're trying to bake cookies and you go, okay, what's the maximum yield from 3 bags of flour? 3 bags of flour is going to yield you this many cookies, but let's say you only have 1 cup of sugar. If you have only 1 cup of sugar, are you going to use all 3 bags of flour? No, even though that could make dozens and dozens of cookies, we don't know if we can use all that 3 bags. So this might be the same thing. This might be 3 bags of flour here and 1 cup of sugar. But we got to look at the other ingredient. What's the other ingredient?
Potassium hydroxide.
Yeah, so we need to calculate the yield from potassium hydroxide. So we got to figure out. I don't know if this is 1 cup of sugar, but we'll soon find out. What is the yield of cookies for 1 cup of sugar? Well, maybe it's not 1 cup. Maybe this is a 50-gallon drum of sugar. Who knows? So we got to figure it out because we don't. And so. So we need to calculate the yield from the other ingredient, which is KOH. And so we're going to go from what? What do you have here? Where do we start this?
Grams of KOH.
Yeah. Okay, how many grams?
43.0.
All right, then finish this. This is where you're going to see where it doubles. But we don't have to factor it in because it's factored in there using dimensional analysis, so I don't have to double it anywhere, except in one spot. You'll see that one spot where it doubles. What did you get? 52.96? You got 105.9? 105.9? Okay, let's see the setup here. So we're going to go from grams of KOH to what?
Grams of H2O.
No, grams of KOH to in the second calculation here. Yeah. So we're going to do 1 mole of KOH for every 56.11 grams of KOH. So grams of KOH cancel. getting the moles of KOH. Then we're gonna go from moles of KOH to what? Yeah, we don't want to go to, H2O would be more convenient, but we don't want to go to H2O because they're asking for potassium carbonate. And so we're going to go from moles of KOH to moles of potassium carbonate. What's the mole ratio here?
1 to 1.
1 over 2.
No.
1 over 2.
1 over 2.
Yeah. And so 1 mole of potassium carbonate for every 2 moles of KOH. So here's where the 2 comes in. See, it's 2 times 5611. But we don't have to do it, you know, because the mole ratio will take care of that for us. So it's always per 1 mole, not per 2 moles or per
Could
2
have,
moles.
you might have done it in the beginning and just put one more.
We could have done it, yeah. And then 138.21 grams of potassium carbonate for a mole of potassium carbonate. So everything cancels except for grams of potassium carbonate. Is this correct? 5296? Is this what other people got? So what this number means is this is, you know, if I use up all my KOH, this is how much I can make. And so this is like, let's say you have 2 ingredients to make cookies. One ingredient can make 48.99. The other ingredient can make 5296. How many are you going to make?
48.99.
48.99. Because we don't have enough. Right? And so what we say is that which one of these is going to be the theoretical yield?
The first.
Yeah. And so this is called the theoretical yield, the Ty. This is called the limiting reagent because we're going to use up all this. So this is the LR. This one is called the excess reagent. And so there's no way we can make 5296 because we're going to run out of the CO2 before we can do that. All right, so we aren't going to use up all of this. It would be nice to do this stoichiometrically because if we did this stoichiometrically, then we use up both. We don't have any waste. Uh-huh.
Do you have a preference on the XS versus the ER?
No, no preference. Either. Excess or ER is fine. ER stands for excess reagent or reactant. And so that's 3, you know, figuring out the theoretical yield, the limiting reactant, and the excess reactant. And then the last step is to figure out, you know, how much of this excess reactant I just wasted. Not only did I just waste it, I have to worry about impurities. You know, when you have excess reactant left over there, then you have to worry about cleaning or removing the excess reactant out of there. And so how much excess reactant remains? Can you do that calculation for me? Yeah. Try to calculate the number based on the equation. What was the equation again?
Unreacted excess equals initial amount minus amount consumed.
Yeah, initial minus the amount consumed. Go ahead and do that calculation. Did you get it? What is it? 3.2? So you have 3.2 grams out of the 43 that are going to be left over. So 3.2 grams of KOH remaining. Is that what other people got? Okay. 3.2. All right, and so the setup here is just that it's going to be 43.0 grams. That's our initial, minus the amount consumed by the LR. The LR is the 15.6 grams of CO2. And then we go from grams of CO2 to moles of CO2. And then from moles of CO2, we're going to go to moles of potassium carbonate. No, not moles of potassium carbonate. Potassium carbonate is a product. We want to go to moles of KOH. And from moles of KOH, we go to grams of KOH. And then we're done. And so we got 43.0 grams. How much was consumed? How many grams was consumed? 39.8. And so it's close. Just a little bit of excess. The little bit of excess is still waste. All right, that's an example of limiting reactant. If we look at the previous problems, we aren't going to have a situation where we have multiple. So for example here, this 4.14 grams of butane reacts with excess oxygen. So they didn't even tell us how much oxygen, they just told us it's excess. If this is excess oxygen, that means all 4.14 grams of butane will react. Let's take a look at some others. Okay, this is a little different there. All right, now we have that. Now we're going to do something. This is what we predict. Theoretical yield is the predicted. But we have something called the experimental yield. The experimental yield is the actual amount recovered. In lab. This varies depending on the experimenter, etc. The day. Sometimes it's not worth it. And so in theory, how many grams of potassium carbonate were we supposed to get? According to our calculations, in theory we're supposed to get 48.99 grams. But let's say you did this experiment and you were only able to recover, let's say, 47 grams. Then we lost a little bit. And so the reason the actual amount varies is due to losses. We lose a little bit. How do we lose a little bit? Because sometimes it's not worth spending 30 minutes scraping every little crystal out. Sometimes you'll go, okay, that's enough. I got most of it. I'll leave a little bit in there because it's just going to take too much time to get. And so what we have here is we have something called a percent yield. The percent yield is equal to the actual yield. Which is this, AY, actual yield. Over the theoretical yield, TY, times 100%. And so, let's say experimenter B got an actual yield of, let's say they were pretty close, 48.1 grams of potassium carbonate. In theory, they should have gotten 48, so they lost 0.8 of a gram. What is the percent yield?
47 over 48.1.
I'm sorry?
47, it's a 47.
No, this is extra. We're going to call this, was this number 47? Let's see. 46. So we'll call this 46Z. Z. 46Z, because this is just an extra add-on to this. And so people, people judge themselves by the percent yield. So one student might get this percent yield, another student might get a higher percent yield. And so the student who got the higher percent yield, maybe they have better technique, maybe they just spend more time. And so this is a number that people often calculate because they want to see how well the experiment went. And so they actually got 48.1. They were supposed to get 48.9 times 100%. So let's see what that percent yield comes out to. 48.1 divided by 48.9 times 100, 98.36%. So 98.4%. And so this student might get, or experimenter B might have gotten 98.4, but experimenter C might have gotten 99.3. You go 99.3% yield's better, because they lost less. Well, student D might have gotten 67%. They get 67%, that's not so great. And so the percent yield varies depending on who conducts the experiment, who did the work. Some reactions, however, have a pretty consistent percent yield. Let's say, you look at it and on average, most people did pretty good. Let's say on average, most people did pretty good, and so we might assign a percent yield. Let's say the average percent yield for this was 98.5%. If the average percent yield is 98.5%, then we can make some predictions. We'll predict the next class, how much they'll get. Why would we want to do that? Well, let's say you're baking cookies or something for an event. We'll just use the baking analogy. And let's say you expect some losses, like some cookies aren't going to look as good or some might break. And so you got to account for some losses. What are the average losses? Let's say maybe 5, maybe you eat some too. And so we'll account for some losses. And so we'll just say the average number of losses is this. So this was determining percent yield. So we just did a calculation where we determined percent yield. Okay, now what we're going to do is we're going to compensate for losses. based on average, some average percent yield. And this average percent yield is somewhat arbitrary. Obviously, it can be quite wrong, depending on who did it. And so let's look at an example calculation here. Let's say you need 100 cookies. But your average percent yield is 95%. So, that means 5% losses. The losses could be a variety of reasons. Let's say you didn't scrape all the batter out of the mixing bowl. Let's say you ate some of the dough or you ate some of the cookies. So let's just say they're 5% losses. If they're 5% losses, how many cookies do you need to make to get 100? And so how many cookies should you plan to make? This is the theoretical yield. What?
105.
How many cookies should you plan to make? Was that theoretical or actual? Plan to make is, let's say, theoretical yield. In order to get an actual yield, of 100 cookies. And so we need 100 cookies. And so in theory, how many cookies do we have to prepare to make?
Right.
106. We'd have to make 106. And so the way we do this is like this. We have to start labeling things with AY and TY. And so it'd go like this. I need 100 AY. And then if I have 95% yield, that means I'm going to have, for every 100 TY, I'm going to have 95 AY for the cookies. We're going to put units on these, like grams or whatever else. And so what is that going to give me? 100 times 100 divided by 95. I need to have 105.26. So I'm going to need to prepare 106 cookies or something like that, right? Or 105.26, 105 and a quarter cookies. So I've got to make enough batter for that. Or five and a quarter, something. It depends if you want to do a fraction or not. All right, so we're going to use this in calculations here, but we're going to do this without the complication of the limiting reactant first. Right, here we don't worry about the limiting reactant. The function of sodium thiosulfate in film photographic developing is to remove excess silver bromide by the reaction. So this is sodium thiosulfate. Thiosulfate is S2O3 -. This is not one you have to memorize, but thiosulfate is actually reacts with the silver bromide. Take a look at this reaction. It's just what you would have predicted. It's what you would have predicted. This to me looks like an AB plus CD. AB plus CD, where A is sodium ions, B is thiosulfate S2O3 2-. CD, silver ions, bromide. What should we end up with? We should end up with sodium bromide, which we did, sodium bromide, and silver thiosulfate. But this is an example of, what did I call this? You saw this before. This is an example of incomplete reaction or partial reaction. And what we have here is, this is metathesis also. This is another reason that I don't like to call it double replacement, because not everything fits that double replacement pattern, because what we end up with is this. How would you name this? You know, this is very simple. What this is that, yeah, sodium silver sulfate. This is an example of mixed cation salt. We have mixed cation salts and we have mixed anion salts. An example of a mixed cation salt, you might have noticed before, is this. What's the name of this?
Iron peroxide.
It's called magnetite. It's a mineral, magnetic. But it would be called what? Iron 4 oxide. Iron 4 Roman numeral 4 oxide. Iron 4 oxide. Well, let's see. We have 3 iron 4s. I'll write Roman numeral here. And then how many oxides? 1, 2, 3, 4. Does that work out? Work out? No. It's over here at 4 times 3 is plus 12. Minus 2 times 4 is minus 8. Plus 12 minus 8 doesn't work out. We've got to rethink this. What's the name of this? What are the common charges on iron? Plus 2 and?
Plus 4.
Plus 3. Plus 4 is common on lead and some of the others, but not iron. Plus 2 and plus 3. So let's go with all plus 2s. Does all plus 2 work?
Yeah.
That gives us plus 6 minus 8. How about all plus 3s? Plus 3 plus 3. 3 times 3 is plus 9. Ah, close.
Plus 3 is more plus 2.
You don't, what is it?
Is it possible to add 2 different?
Yeah. Right. 2 different ions. So if we do, let's see, if we do 2 plus 3s like this, and 1 plus 2, does that work? Yeah. You know, a lot of people, because the way we did it before, this is the way we figured out the charges before. I know what you're doing because you're taking the ratios. The way we figured out the charges before is like this. So minus 8, and therefore this has to be plus 8. This has to be plus 8 to cancel out that minus 8, so it adds up to 0. And so each one must be 8/3. Plus 8/3. What is 8/3? Well, 8/3 is 2 and 2/3. And so this should be iron 2 and 2/3 oxide. If you did this the way we've been doing it, you would call this iron 2 and 2/3 oxide. But does that make any sense at all? Oh. This doesn't make any sense at all. And the reason is because you're absolutely right. This is what we call mixed cation salt. This is metathesis. So we need 2 iron 3s and 1 iron 2, and they gotta come together to form this precipitate. And so the same thing here. This is called mixed cation salt. And so we need 3 sodiums and 1 silver to come together to form this precipitate. And so this is metathesis. Metathesis can get a little trickier. This is why I don't call them double replacements, because double replacements it doesn't always fit the double replacement pattern. You know, not everything fits the double replacement pattern. And so I just like, well, does this fit the ion combination pattern? Yeah, this fits the ion combination, because we're going to combine 3 sodium ions, 1 silver ion, and 2 thiosulfate ions. They're going to combine to form a precipitate. These favorable ion combinations, I need metathesis for that. Well, let's go back to this one. What is the percentage yield if the reaction is 8.18 grams of sodium thiosulfate produces 2.61 grams of sodium bromide? So they give us the sodium thiosulfate, which is this, but they didn't tell us anything about silver bromide. So we have to expect that silver bromide must be in excess. And this is the yield. Well, it produces this much. Well, that is the actual yield. If the actual yield matches the theoretical yield, then we had 100%. Well, we got to find out. So the first calculation is we got to calculate the theoretical yield from 8.18 grams. So we'll go 8.18 grams of sodium thiosulfate. Let's square out over time. To moles of sodium thiosulfate, moles of sodium thiosulfate to moles of sodium bromide to grams of sodium bromide. And so that would be the theoretical yield. We calculate the theoretical yield based on stoichiometry. So the theoretical yield is the yield based on stoichiometry, the calculation. And the actual yield is what they actually got, 2.61 grams. So let's just take a quick look at this and we'll take a break. So the first thing they did was calculate the what they call the ideal yield, or the theoretical yield. So grams of sodium thiosulfate to moles of moles of sodium thiosulfate to moles of sodium bromide to gram. And so in theory, they should have gotten 2.66 grams of sodium bromide. This is ideal yield. In actuality, they lost 0.05 grams. Do you see that?
Yeah.
They lost it. And so they only got 2.61 grams, the actual, over the ideal or the theoretical yield of 2.66, which makes a 98.1% yield. Well, 98.1% yield is pretty good. That's not bad. We would say that's pretty good. Okay. All right, let's take a break here and then we'll start up.